long time ago, a promising young engineer named Arseny was working for a ride-hailing company. He was tasked with an ambitious project: build a system to estimate a ride's fare before the trip even started. The old model was simple, just a formula based on time and distance. But the company wanted something smarter, something predictive, to give both the driver and the passenger certainty up front. It seemed straightforward. Arseny thought, all we need is a simple model that uses geo features from a map service and wrap it in a microservice. Easy. He was so confident, so sure of the path, that he didn't even bother writing a design document. It was a log bridge over a small creek. What could go wrong? What went wrong was everything. The geo features weren't nearly enough for an accurate estimate. More complex features required an advanced infrastructure that didn't exist. As the model became more sophisticated, its predictions became wildly unreliable, sometimes too high, sometimes too low. The errors weren't random. The model was biased against certain types of trips. The executives wanted to override the model's predictions for special promotions. But the system wasn't built for that. Too much time, too much money, too much code was spent building a model that didn't actually solve the real problem. By the time all the issues were finally wrestled to the ground, the market had changed. The project, that simple log bridge, was scrapped. It was a failure. A failure born not from a lack of skill, but from a lack of a map. A failure that could have been avoided if someone had just read a book like this one. Today we are talking about that book. It is the map that Arseny and so many of us desperately needed. The world of machine learning is drowning in noise. Every day, a new groundbreaking algorithm, a new state-of-the-art model, a new framework promises to change everything. We are taught the intricate mathematics of neural networks, the clever tricks of gradient boosting, and the elegant logic of support vector machines. We practice on clean, curated datasets from Kaggle competitions and academic papers. And with this arsenal of knowledge, we feel ready. We feel like master swordsmiths, capable of forging the most powerful blades imaginable. But then we step out of the dojo and onto the battlefield of the real world, and we realize a terrible truth. Knowing how to forge a perfect sword is completely different from knowing how to win a war. This is the central, agonizing problem that machine learning system design by Valery Babushkin and Arseny Kravchenko confronts head-on. The book exists because of a massive, painful gap that plagues the entire tech industry. The gap between knowing machine learning algorithms and knowing how to apply them effectively to build real-world systems that create actual business value. It's the gap between the scientist in the lab and the engineer in the trenches. The authors, a Kaggle grandmaster and a seasoned ML engineer who have collectively spent decades in those trenches at companies like Facebook, Alibaba, and countless deep tech startups, saw this gap firsthand. They saw brilliant minds, people who could recite ML textbooks backward, struggle and fail. They saw projects with immense potential crumble, not because the models were bad, but because the systems surrounding them were brittle, misguided, or non-existent. They saw teams building scattered, isolated components that could never be assembled into a functioning, reliable whole. This book is their answer. It is their grand promise. The promise is not to teach you another algorithm. It is to give you a comprehensive, end-to-end framework, a battle-tested philosophy for designing, building, releasing, and maintaining ML systems of any scale. It promises to be the guide that takes you from a vague business problem to a robust, scalable, and value-generating system that doesn't just work on paper, but thrives in the chaotic, ever-changing reality of production. It's a book about asking the right questions before you ever write a line of code. It's a book about building the entire war machine, not just forging the sword. Babushkin and Kravchenko aren't just giving you a collection of tools. They are handing you the master blueprint, the strategic manual that will allow you to navigate the complexities, avoid the hidden pitfalls, and ultimately succeed where so many others have failed. They are giving you the map Arseny wishes he had all those years ago, and the very first, and perhaps most important, commandment handed down by Babushkin and Kravchenko is this: thou shalt explore the problem space before ever setting foot in the solution space. This sounds simple, almost trivial, but the authors argue that violating this commandment is the single most common reason that machine learning projects fail. We, as engineers and problem solvers, are conditioned to jump to solutions. A manager comes to us with a request, and our minds immediately ignite with possibilities. Oh, we can use a transformer model for that. I'll use a vector database? We need a real-time API? We are, as Abraham Maslow famously said, like a person with only a hammer, treating everything as if it were a nail. The book introduces us to a young, meticulous engineer named Steve. Steve's boss, Linda, comes back from a meeting with the VP of Sales, Jack. Jack's team is overwhelmed with customer leads and can't handle them all. He has an idea: can the ML team build an AI solution to automatically rank leads from best to worst, so his team can focus on the most profitable ones first? Steve, being a good engineer, immediately starts asking questions. What's the deadline? How big is the data set? What accuracy do we need? What's the maximum time allowed to score a lead? He gathers this information and heads back to his desk. His mind is already racing. Okay, this looks easy. We can frame it as a ranking or classification problem, craft some features, train a model, expose an API, integrate, and deploy. But then he gets stuck on two questions. What's the best classification method for this? And how should he integrate his Python code with the company's CRM system? 3 hours later, his browser is a graveyard of tabs on few-shot learning techniques and CRM API documentation. He has made a critical mistake. Every single one of his questions was about the how. He never stopped to deeply question the what and the why. He was lost in the solution space. The problem space, the authors insist, is where true success is born. It's the realm of why questions. Why do we need to build this solution? What problem at its absolute root does it solve? Why does this problem even exist? What are the alternatives? Why do we think machine learning is the answer at all? It's about understanding the context, the messy reality behind the clean request. Maybe Steve should have asked Jack more questions. Questions like, how do your best salespeople currently identify a promising lead? What's their gut feeling based on? What happens if we misclassify a good lead as bad? What's the cost of that mistake? What if, instead of ranking, we built a simpler system that just filters out the 95% of obviously bad leads with a few simple rules? Would that solve the immediate problem of your team being overwhelmed? By focusing only on the solution space, Steve missed the bigger picture. He didn't know if a third-party plugin for the CRM already existed that could solve this problem for a few dollars a month. He didn't know if the cost of a mistake was so high that a black box model would be too risky. He didn't know that simple, rule-based heuristics could have provided 80% of the value for 10% of the effort. He was so focused on building the perfect hammer that he never stopped to ask if the problem was truly a nail. This is a trap that ensnares countless projects. We build incredibly sophisticated, technically impressive solutions to the wrong problems. The book's first great lesson is to force ourselves to become detectives before we become architects. To live in the world of the user, the stakeholder, the business, to understand their pain so deeply that the shape of the true solution begins to reveal itself. And often, that solution is far simpler and more elegant than the one we first imagined. The second core idea, which flows directly from the first, is the author's elevation of the design document from a bureaucratic chore to the single most critical artifact in the entire ML system lifecycle. For many engineers, the phrase design document conjures images of dusty, 100-page specification binders from old-school waterfall projects, something to be endured, not embraced. The book passionately argues against this perception. It presents the design doc not as a static blueprint to be followed blindly, but as a living, breathing thinking tool. It is the crucible in which vague ideas are forged into a coherent, actionable plan. It's the process of writing the document, the authors claim, that is everything. They begin by systematically dismantling the common myths. Myth A1: design docs are only for big companies, not agile startups. False. The authors argue that the act of writing down a plan, even a short one, forces a startup to uncover blind spots and align the team, which is critical when speed is everything. A simple, shared note can be enough to prevent weeks of wasted work going in different directions. Myth A2: they're only for complex projects. False again. Even a simple project benefits from a document that defines the scope and prevents scope creep, where every stakeholder is tempted to add just one more little feature. Myth A3: every design doc should follow a rigid template. This, they say, is a path to bloated, unread documents. The template should be minimal, a core skeleton that is extended only where necessary. And the most profound myth they bust is myth 5-4 every design document should lead to a deployed system. The authors state a radical but powerful truth more often than not. A good design document leads to no ML project at all. And this is a success. Imagine spending 2 weeks meticulously outlining the goals, the risks, the data requirements, the validation strategy, and the potential solutions, only to realize that 90% of the desired business outcome can be achieved with 2 simple IF statements. That realization, born from the structured thinking the design doc forces upon you, just saved the company 6 months of relentless, expensive, and ultimately unnecessary work. The design document is your first and cheapest line of defense against solving problems that don't need solving. To make the design doc even more powerful, they introduce the concept of anti-goals. While goals define what your system should do, anti-goals define what it should not do. This is a brilliant technique for sharpening focus. If you're building a recommendation engine for a small boutique store with only a few hundred items, a crucial anti-goal is this system will now be built to scale to millions of items. Stating this explicitly prevents engineers from over-engineering a solution for a problem that doesn't exist. It frees the team to focus on what truly matters, in this case, perhaps, the quality and diversity of recommendations, not the raw throughput. Throughout the book, the authors build 2 separate, detailed design documents for fictional companies, Supermargertail and Photostock Inc. We see these documents evolve from chapter to chapter, from a high-level problem definition to detailed sections on metrics, validation schemas, and baselines. This isn't just a theoretical exercise, it's a practical demonstration of the design doc as the central repository of collective knowledge, the shared brain of the project. It becomes the place where tough questions are asked and answered, where trade-offs are made explicit, and where the entire life cycle of the system is contemplated before the first building block is laid. It transforms from a mere document into the very heart of the machine learning system design process. Once you've defined the problem and sketched the blueprint, the temptation is to build the most advanced, powerful, state-of-the-art model possible. We want to show off our skills, to use the latest and greatest techniques. This is where Babushkin and Kravchenko introduce their third, and perhaps most humbling, core principle: the supreme power of the baseline. Before you build your gleaming, chrome-plated, multi-layered neural network, you must first build the simplest possible thing that could possibly work. You must build a log bridge. A baseline, in the author's philosophy, is more than just a simple model. It's an MVP for your entire system. Its goals are threefold. First, it's a placeholder to check that all the other components of your system, the data pipelines, the API, the monitoring, are actually connected and working. It's a smoke test for the whole infrastructure. If you can't get a model that just predicts the average value to work in your system, you have no hope of getting a complex model to work. Second, it's the benchmark against which all future, more complex models will be judged. It is the zero on your coordinate plane. It's shockingly common, the authors note, for teams to spend weeks on a sophisticated model only to find it barely outperforms a simple heuristic. The baseline keeps you honest. And third, it's your ultimate fallback. When your complex model inevitably fails in production due to unexpected data, a bug, or cosmic rays, the system can switch to the simple, reliable baseline. A mediocre prediction is almost always better than no prediction at all. The book champions a progression of simplicity. You start with a constant baseline. For a regression task, this could be simply predicting the average, or the median, or the value from last week. For a classification task, it could be always predicting the most common class. The authors tell a fantastic story of Valeri's colleague, who won a Kaggle competition on time series forecasting with nothing more than a stepwise constant baseline, much to the frustration of competitors who had spent months engineering hundreds of features for their complex gradient boosting models. This isn't to say complex models are useless, but to prove a point, you must first earn the right to use them by proving you can beat the simplest possible solution. From the constant baseline, you move to a rule-based baseline. This might be a few simple if-then statements. For a taxi fare prediction, it could be: if the destination is Manhattan, predict 4 minutes. Arseny notes that this exact type of baseline was actually used in production for a while as a fallback at one of his previous companies because it was so hard to beat reliably. Only after you've exhausted these do you move to a simple machine learning model, like a linear or logistic regression. This philosophy extends to features as well. Instead of starting with hundreds of complex, engineered features, you start with the bare minimum, a handful of the most obvious, easy-to-calculate features. Then you incrementally add interactions, aggregations, and perhaps embeddings, measuring the value of each step. This deliberate, incremental approach to complexity acts as a powerful governor against the natural engineering tendency to overbuild. It forces a ruthless focus on the trade-off between effort and accuracy. The book presents a graph showing this relationship in the beginning. Small amounts of effort yield large gains in accuracy. A constant baseline is easy to build. A rule-based baseline takes a bit more effort, but significantly improves the metric. A linear model adds more effort and more gains. But soon, you hit a point of diminishing returns. A complex gradient boosting model might require more effort than all the previous steps combined, but only eke out a tiny, fractional improvement in the metric. Is that fractional improvement worth the massive increase in complexity, maintenance cost, and training time? The baseline gives you the data to make that decision rationally, not on ego. It's a powerful tool for fighting what the authors call the complexity bias, the insidious belief that a more complex solution is inherently a better one. The final piece of the puzzle, and the one that truly separates a robust, long-lasting system from a fragile one, is the book's focus on the post-launch lifecycle. An ML system is not a static artifact that, once built, is finished. It is a living organism that exists in a dynamic environment. The authors stress that your work isn't done at deployment. It has only just begun. The fourth core idea is that a system's success is determined by its immune response, its ability to detect and adapt to change through rigorous validation and relentless monitoring. First, they tackle validation. The standard train validation test split is presented as just the beginning. The book delves into the nuances of choosing the right validation schema for the right problem. For time series data, you can't just randomly split your data. You must respect the arrow of time, using rolling cross-validation to simulate how the model will perform on future, unseen data. For data with grouped structures like multiple transactions from the same user, you must use grouped validation to prevent the model from learning user-specific patterns that won't generalize. They even introduce more advanced, almost adversarial techniques. What if your labeled training data and your unlabeled production data come from different distributions? A standard validation set won't tell you how your model will perform. The book suggests adversarial validation, where you train a classifier to distinguish between your training data and your production data. If the model can easily tell them apart, you have a distribution mismatch, and your validation results are likely overly optimistic. This kind of deep, critical thinking about how you measure performance is what separates amateur work from professional engineering. But validation only tells you how the model should perform. Monitoring tells you how it is performing, and more importantly, when it starts to fail. The book presents a pyramid of monitoring needs. At the base is software system health, basic things like latency and error rates. Above that is data quality and integrity. Is the incoming data schema correct? Are there suddenly a huge number of missing values? The authors tell a story from one of their friends who was building a computer vision system for an augmented reality app. The team was based in St. Petersburg, Russia, a city famous for its overcast, cloudy weather. Most of their test data was gathered there. But when the company's investors, based in sunny Cyprus, tested a pre-release version, the model performed terribly. The system wasn't built to handle the harsh shadows and bright sunlight of a Mediterranean climate. This is data drift. The statistical properties of the production data have drifted away from the training data. Even more insidious is concept drift. This is when the underlying relationships in the world change. The meaning of the data itself shifts. The book uses the example of a model that predicts whether a user is in a high-tax bracket. If the government suddenly changes the tax laws, the income threshold for that bracket changes. The model's input features might look the same, but the ground truth labels are now different. The model, trained on the old reality, is now obsolete. Without monitoring for these drifts by tracking feature distributions, prediction distributions, and the final model accuracy against ground truth labels, the model will silently degrade, making worse and worse decisions until it becomes not just useless, but actively harmful. The book provides a framework for reacting to these drifts, from simple retraining to more complex strategies like creating separate models for different data segments or adjusting business logic on top of the model's output. This continuous cycle of validating, monitoring, and adapting is the heartbeat of a healthy ML system, ensuring it doesn't just survive its launch, but evolves and continues to provide value for years to come. So, what makes machine learning system design truly different from any other book on the shelf? It is its relentless, holistic focus on the entire life cycle, framed through the practical, hard-won wisdom of its authors. It is not an academic textbook of algorithms. It is not a niche guide to a specific MLOps tool. It is a strategic field manual for the working engineer. Its unique perspective comes from the seamless blend of high-level, almost philosophical principles like problem space before solution space with granular, in-the-weeds tactical advice, like using Poisson Bootstrap for creating confidence intervals on metrics or using adversarial validation to detect dataset shift. The campfire stories scattered throughout the book are its soul. These aren't contrived examples. They are real, often painful, lessons learned from years of building real systems. They give the book an authenticity and a sense of shared experience that is incredibly rare in technical literature. This book is explicitly for the mid-career engineer, the senior engineer, and the engineering manager. It's for the person who knows the ML basics, but is now facing the daunting task of building a real, production-grade system. It's for the person preparing for a grueling ML system design interview at a top tech company, as the entire book is structured around the very thinking process those interviews are designed to test. It is, however, absolutely not for the beginner. The authors are clear. They expect you to understand the fundamentals of machine learning and applied programming. This is not a Learn ML in 24 hours guide. It's a graduate-level course in the craft of building. The single most valuable takeaway a reader will be left with is a fundamental shift in mindset. You will stop thinking of your job as building a model and start thinking of it as designing a system. You will internalize that the model is just one cog, and often not the most important one, in a much larger machine. You will learn to love the messy, human-centered work of understanding the problem, the meticulous, architectural work of designing the solution, the disciplined, iterative work of building simply, and the vigilant, unending work of maintaining and monitoring the system in the wild. Let's return to Arseny's story of the failed ride-hailing app. He set out on a journey with supreme confidence but no map. He got lost in a forest of unexpected complexity, wasted precious resources, and ultimately, never reached his destination. This summary you've just listened to is only a glimpse of that map. It has shown you the major continents, the key mountain ranges, and the most treacherous rivers. But to truly navigate the journey yourself, to understand the contours of the land and the hidden paths through the woods, you must immerse yourself in the full experience. This book, Machine Learning System Design, is that journey. It is your opportunity to learn from the mistakes of those who have walked the path before you, to absorb their wisdom, and to arm yourself with the principles and practices that separate success from failure. The decision now is simple. You can continue to forge ahead with a broken compass, armed only with algorithms, hoping you don't get lost. Or you can invest in the map. You can equip yourself with a framework for thinking, a guide for building, and a philosophy for creating machine learning systems that don't just work, but last. To truly understand this, you have to let the author's words, their stories, and their hard-earned lessons wash over you. The link to the book is in the description below. Get it, read it, and start building.